So before we can begin to prove this theorem, we need two things. We've already seen lots of circles and triangles in this drawing, so it makes sense that we would need something relating the angles of a triangle to the arcs of a circle. The second thing is less obvious. There are some shapes hidden in this drawing with four sides, so we'll need something relating to the angles of a quadrilateral whose vertices are all in the same circle. So to find the first lemma, that's what a previously proved starting theorem is called. We start with the circle, and 3 points on the outside of that circle. Let's call them A, B, and C. We want to know the angle A in terms of the angle from B to the center of the circle to C. We'll call this angle X. The first thing we notice is that the lines from the center to B and C are radii, which means that they're equal. This doesn't get us anywhere on its own, so we draw the radius from the center of the circle to A. Now we've broken A into two angles, alpha and beta. And since the two triangles we've created are isosceles, the angles at the bottom of our image are also alpha and beta. Since every triangle has inner angles adding to 180 degrees, the central angles of our triangles are 180 minus 2 alpha and 180 minus 2 beta. We now see that the central angles add to make a full circle, which has 360 degrees. Therefore, 180 minus 2 alpha plus 180 minus 2 beta plus x equals 360. Some simple algebra shows that x equals 2 alpha plus 2 beta, which is equal to the 2 times the angle A. Therefore, x over 2 equals angle A. In order to get the second lemma, we're actually going to use the first. Start by drawing a circle. Then draw a quadrilateral A, B, C, D inside it, with each of the four vertices on the circle. This is called an inscribed quadrilateral. By our first lemma, we know that angle A equals 1/2 arc BDC, and angle C equals 1/2 arc BAD. Look at those arcs. When you add them together, you get a full circle, which means they add to 360 degrees. That means when you add together angle A and angle C, they have to give you 180 degrees. This is just the result we want, that opposite angles of an inscribed quadrilateral are supplementary, which just means they add to 180 degrees. Sadly, we are not done. Only part of the second lemma has been proved. We need to prove that the converse is also true. That is, if opposite angles of quadrilateral are supplementary, then the quadrilateral is able to be inscribed. Again, we'll start with a circle and a quadrilateral A, B, C, D. This time, only 3 of the points, A, B, and D, are guaranteed to be on the circle. We can be sure that 3 of the points lie on the same circle because any 3 points define a circle. Consider the case where point C is inside the circle. We know by our first lemma that angle B is half of the arc between A and the extension of BC to meet the circle, and angle D is half of the arc between A and the extension of DC to meet the circle. Notice when you add these arcs, you do not get the full circle. Therefore, their sum is less than 360. This means that half of their sum has to be less than 180. Likewise, when C is outside of the circle, angle B is equal to half of the arc between A and where BC meets the circle, and angle D is equal to half of the arc between A and where DC meets the circle. When you add these arcs, you get more than the full circle, meaning their sum is greater than 360, and half their sum is greater than 180. Since we've considered the only possible cases where a quadrilateral is not inscribable, and shown that the opposite angles cannot be supplementary, we've proved our lemma.